warping happens on a larger scale. So many of these folded mountains can happen, a syncline and an anticline, or individual mountain ranges can happen on small regional areas. Warping happens over a larger section, like the Canyonlands National Park, and it creates these huge gently folded basins or domes. That was short, and now we're on to faulting. Okay, so the stresses that cause these fractures, the stresses that cause these fractures are the same things we talked about earlier, as far as tension, compression, or shear stresses. But it happens when the movement, the plate movement, is fast, so that instead of just folding or warping, the rock surfaces crack. Or it happens because the material itself, the sediment, the rock layers, are too rigid. They're not as bendable. So when we have tension, so that would be divergent plates, the result of the type of fault or crack that happens, fracture, is called a normal fault. When we have compression, which would be convergent plates, the type of fault is called a reverse fault. And then when there is shear stress or shear stress, you get strike slip faults. So let's look at each of these. So a normal fault is the kind where there is tension, where there is divergent plates, so one plate's moving to the left, the other, I'm going to go west, one plate's moving to the west, the other plate's moving to the east. And when that happens, the fault that is created is this crack along the landform. And with a tensional fault, part of the land drops down. So you can imagine, as you're thinning out the land and stretching it, this section here drops with the stretching movement, and it creates what's called a fault scarp, which is the back edge of this landform. So this piece of land would have been up here at the top. This has been pulled down or has dropped down as the sediment and the earth has been stretched. And the angle between the surface and the fault scarp is a very obtuse angle. It's a very big, wide open angle. And that's one of the ways, or one of the components that would help you identify whether it's a normal fault or a reverse fault. So again, that normal fault is a diverging plate. The result is tension in the surface. You get this fault scarp with an open, wide angle. You get vertical displacement of the land, so the land actually drops down in elevation. The crust gets thin, and some very famous examples of this type of faulting is in Oregon, in the Basin and Range, in Nevada, and in the African Rift Valley. So here is an example of some of the landscape. So back in the background here, this is a fault scarp. This is a tensional crack that happens when the land is being pulled apart, and you can see that much of the land surface was basaltic lava, and it creates these specific landforms called a basin and range. So as this block of earth is being stretched east and west, you get sections of the landscape that drop down, and you can see the displacement. If you were to follow this layer of sediment, it has now been dropped down to here, That's called the offset. So here is a layer of, say, limestone, which used to be connected, all of these white layers, and now this layer of limestone has dropped down. The block of sediment in a basin and range that is dropped is called the graben, and the relative uplift of that is called the horst. So you get the specific landscape called the horst and graben. The western U.S. is subject to these tensional cracks, and I wonder if I can zoom. Let me see if I can zoom that. Oh, that's pretty cool. So if I zoom this in a little bit, you can kind of see these ranges or these ridges that are a result of the continental plate being stretched a little bit in this east-west direction, creating these linear mountains with these grabens down in between. And then, I don't know if I can put that back now. Wait. Come on. Here we go. And then on the surface, besides the large scale horst and graben and fault scarps, you're going to see tensional cracks. So as the land is being pulled apart, you may see these lines of cracking in the surface. And in some of these areas, these grabens or basins historically have been filled with internal lake sediments and lakes. So in Oregon, if I can go back, let's see, what is that one? No, I'm going to go here. In Oregon, in this area, this is Fort Rock, Christmas Valley, and these areas have some. In fact, we looked at the image of Fort Rock, and remember that those were historic lakes. So often in these grabens, when you would have snow up on the horst or rainfall, it would collect in these internal basins and create these very deep, internally drained lake systems. And that was what Fort Rock was part of. It's part of the basin and range, and it was in one of these grabens. The African Rift Valley is the result of tectonic movement pulling the continent to kind of the northwest and the southeast, and opening up all of these lakes and volcanic features that happen as the result of those tensional areas. And so here is part of that tensional cracks that are filled with water in the African Rift Valley. And this is a small fault scarp, and so you can see that the angle is obtuse. If I look down at the back part of this fault and then the surface, so the fault has dropped down, and there's in Eastern Oregon, there's a lot of monitors recording what is the angle of the slope, how fast are these moving. So one way to identify earthquake or faulting movement is the displacement of the strata. So originally, if we look at the law of superposition, you have the older sediment or strata at the bottom and the younger sediment strata at the top, and often that material is deposited in a very flat kind of pancake, layer cake formation. And then if there is some offset where in this one we're missing the E strata on this side, so this block has been moved up and the E strata that was here has been eroded at some point in time, and so that there's just a remnant left. But you can see the offset where this layer and that layer should stay connected. And you can see that this is down in Coos Bay, looking at some of the cliff walls along the beach, and you can see a small offset here. I think this is about an inch offset. So there was some kind of faulting that happened that moved this sediment with respect to that layer. And you can almost, this one's an easy one to match. So at some point when this sediment was deposited, this was a straight layer and these were connected, and this flame structure here as well had been connected. So you know that there is some faulting, some movement within that structure. And here's a larger displacement. So you can match this layer of clay sediment with this layer, and just given this surface, it's not possible at this point, because I don't know exactly where this was, but whether this was a normal fault or a reverse fault. But you can also see along the fault line right here, this crack, sediment has gotten in here. There has been some iron sediment and sort of rust formation. So the second type of fault is a reverse fault, and this is caused by convergent plates, so kind of squeezing together. So again, instead of pulling things apart where something's going to drop down below, when you have compression, one piece is going to pop up above the other, and this is the cause of the crust getting thicker. And large mountains are built in this way, like the Himalayas or Himalayas. And the fault scarp, when you have an original movement, that fault scarp can cause an overhang, but the angle between the portion of land that has been elevated and the original surface is an acute angle than a wide open obtuse angle. And so that would be the compression of convergent plates. And again, this is very common in the Himalayas or Himalayas, as you have the Indian plate moving to the northeast and the Eurasian plate moving to the southwest. And as those two continental movements come together, the crust gets thicker. So remember back to plate boundaries, when you have two thick granitic continental crusts coming together, you get much thicker crust. So nobody is subducting here. These are both lighter granitic sediments, and they're ramming into each other. I don't want to do that one yet. That seems to be out of order, so we'll go back to that. So in the San Fernando earthquake in 71 caused huge damage, and you see some local displacement. So here was this part of the road was shoved under this part of the road, so it looks a little like you would expect kind of some kind of local compression at this section. Now this was not a compressional quake, this was a strike slip fault, but you can have some smaller scale movement, and so here you have this part of the road overshot and crunched up over that part of the road. So in 1970 there was an earthquake in Peru, and it was a 7.8 quake, so we'll talk about that Richter scale measurement, that 66,000 people were killed in that quake, and this was a result of local subduction, so creating an entirely different kind of movement. So that would have been compression quake, but you have seafloor compression where it's subducting underneath the continental plate. And that's another type of compression, and you get coastal mountains. But that movement, the faulting and strain that causes these huge coastal quakes. The earthquake in the San Andreas Fault, or the fault created along the San Andreas, is a strike-slip fault. And this, sorry, it keeps flipping back. So we have subduction off the coast of northwest U.S. and Canada as a result of this small little plate called the Juan de Fuca plate, which is subducting underneath the continental plate. And then we've got the Pacific plate, which is moving in a basically northwest direction. And then you've got the piece of the North America plate, which is moving a little bit in the southeast direction. And so those two plates are causing this sliding past each other. And with that, you don't get a lot of vertical movement. You get mostly side-to-side destruction. So there's not a huge amount of mountain building. But you can see this ridge is a bit offset. So part of the plate caused these two mountain ridges to split. You can see that this erosional drainage band here is not as linear as it should be. It's kind of offset to the right up here in that image. One of the keys to strike-slip fault is, like as I said, this horizontal offset instead of a vertical offset. So this is a crop field after the earthquake along the San Andreas, and these crop rows would have been perfectly linear. And then you can see that either these rows were sent to this portion of the row was sent over to the eastern part of the image, and this part of the rows was sent to the western, or vice versa. But you can see that they're no longer straight lines. That was also really evident along many of the center lines of roads. So there's no vertical offset here, but you have a good horizontal offset of about, I think it's about 5 inches or half a foot, where the land has been moved sideways.